so today we're going to talk about motion down an inclined plane, and I don't know if Mr. Smigalski's talked at all about this at all, but I'm going to give you some new formulas today. Nate, I've started. Kate, Billy. Guys, I've started. Okay, thanks, Nate. Moving on. Normally, I start this lesson with going to this link, and when I went there, I got nothing. So there's probably a flash upgrade or something that needs to happen here. It's not crucial, but looking at this picture here, usually what I do is I show how when this ramp decreases, right? Can you see the little green sort of triangle thingy here? Oh, I need to do my orientation here. Let's do this first. Okay, Nate, don't start. Okay, Nate, here we go. Okay, so what I was saying is, as that ramp decreases, as it goes down like this, you should see this little triangle sort of disappear, right? Okay, so that's kind of the main idea of that graphic that I can't seem to get up and going here, but I'll see if I can get it for you guys a little bit later. It might make more sense when I'm done, I'm not sure. Anyway, so today we're going to calculate forces acting on an object resting on an inclined plane, like this one right here. We're going to draw this picture. We're going to include the normal force, friction, components of the gravitational force, mg, and calculate the components of F gravity exerted on an object resting on an inclined plane. So we're going to do that. I got to get rid of some stuff here because this is driving me nuts in behind here. All right. I don't think you need to draw that just yet, but you should do. These are notes, by the way, so if you want to write these down, you can. If you want to just print them out later on Schoology, you can do that. Whatever works best for you. Okay? So, when an object sits on a flat surface, you know two things. You know that gravity acts straight downward, and I like to call that FW. It's sometimes, that's FW, weight force. Some textbooks refer to that as FG, force of gravity. Some texts refer to that as FMG, mass times gravity. There's a variety of different ways to write it. I prefer FW, it's just what I do. Okay? So that's FW, and the surface exerts a normal force. Now, just about every textbook is going to show that as FN. Normal force. Normal means perpendicular. It doesn't mean, normal kind of thing. Nate, what you up to? Okay. That's what I thought. Thanks for being honest. Some books will show it as F perpendicular. I actually prefer phones up like that because then I can see when you're on it. F perpendicular is the other one that they use, okay? The question is, what happens when the surface is at an angle? And I'm going to see if I can do this here. If I take this picture right here, and I go like this, what happens? Well, you'll notice that I turned the whole thing, right? But gravity always acts down. Right? So that one sort of changes. But the normal force, or perpendicular force, is always perpendicular to the surface, which is now this way. And you'll notice that in green, this FW, which is down, and the F perpendicular, which is sort of off, cockeyed kind of thing like that, are they balanced? They are not. And what happens when you've got an unbalanced net force? You get starts with an A, acceleration. You get an acceleration. And if the object is at rest, that acceleration is going to cause it to move. Exactly. Which way is it going to move, Kurt? Down the ramp. Exactly. We're going to get a movement down the ramp. So it's actually gravity that's pulling it down the ramp. Okay? Let me go through that all again. I'm just going to put this back to flat. Well, that's exactly what we're going to do today. Okay, so what I was saying is, when it's flat on a surface like that, like look, for example, at my laptop on the table there, or a book on a table, or anything that's sitting on a table, the weight force is going to be balanced by the normal force. Object doesn't accelerate. When I put it at an angle, like so, the weight force is no longer straight. Well, it is straight down, right? The weight force is like that, but the normal force, because it's perpendicular to the surface, it's not opposite weight force. It's perpendicular to the surface. So it's like that, and because I have those two now, right? If I take this one here, I can't. Oh, I can. Excellent, right? And if I add them vectorially, I haven't done it very well because the net force should be which way? This should be a little bit more like this. The net force should be down the ramp. That make sense? How's that sound to you guys out there? Yeah? A little confusing? I will definitely do a little example. Okay? I'm just sort of leading into it here. They may not, no, they won't be numerically equal. They won't be, but even if they were, they would still be because of the direction. But they won't be. Okay, so when an object sits on an inclined plane, Cole, put the phone away and listen, man. Just listen. Mom can deal without you for at least a half an hour. Okay? I'll tell her that when she comes in to see me. When an object sits on an inclined surface, Nate, gravity acts straight downward, Fw, and the ramp exerts a normal force Fn. Like that. Okay. The quantities Fn and Fd, which I haven't talked about yet, are simply the components of the weight force. So, because... Pardon me? There's lots of F's. F just stands for a force, right? And then the little letter is what kind of force. Nate, am I going to have to explain this all just to you individually later? Okay, good. Okay. FD is this one here. I call it FD. It's my own little creation. It's probably got another name in other textbooks. I call it FD for down the ramp. It's not that, yeah, down. FD for down. Okay? Some textbooks will take the whole thing and they will, you know how you've got like your X and Y, kind of like X and Y, kind of like that, and they'll take that and they'll turn it like this and they'll define the X as being up and down the ramp and the Y being perpendicular. It gets a little confusing, I find, doing it that way. Okay? So the quantities Fn and Fd are simply the components of the weight force. Fd pulls it down the plane. And the Fn affects the friction. Now, I haven't really shown you where this Fd comes from. That's on the next slide. It has to do with gravity. It's the component of gravity that acts down the plane. Exactly. See, and yeah, I agree. Yeah, it gets confusing, Kurt. Yeah, I don't like that sort of setup. Okay, so what we're gonna do is we're gonna come up with formulas for FD and Fn. That's what we're gonna come up with. That's sort of what you have to be able to apply today. I'm just showing you the background where it comes from. Okay, am I good to go here? I'm gonna post these later, so if you do get behind, that's fine. Okay, so from that triangle, if this triangle right here, right, this Fn and this little triangle right here, which you may have seen, that's the one I was talking about way at the start. See right here? Same triangle, right? Just flip the other way, that's all. Okay, so from this triangle here, this blue and green one right here, right? From this triangle, this is the part you need to write down. If you're not writing anything down, write this one down. Okay. If I make the angle of the ramp theta, do you see that this theta here is equal to that theta there in that little diagram? Do you see that they match the same? If I go back, this theta here is equal to that theta here. Does that make sense? And as this gets steeper, as that gets steeper, what happens to this angle here? Does it get wider as well? Absolutely, right? That's what I'm trying to show you on that front page that I couldn't show you today. And as the ramp gets flatter and flatter and flatter, the green and the blue lines here are going to get closer together, right? So this theta right here and this theta right here are equal to each other. Okay? The theta, the angle of the ramp, is equivalent to the angle in this triangle right here, which is this triangle right here. Now, this weight force is straight down. Gravity, Fw, is straight down, right? And this normal force here is balanced by, I call this force here Fn. It's really the component of gravity that is opposite to the normal force, right? It's the part of gravity that creates that normal force. It's the part of gravity that pushes against the surface, and then the surface pushes against. So this Fn right here and this Fn right here are numerically equivalent, just opposite direction. For the sake of simplicity, I just call this one right here Fn. Okay? But again, it's really the component of gravity that acts opposite to the normal force. Okay. And then this Fd is the actual force that pulls it down the plane. Okay. I've done setting up all the blocks kind of thing. From this triangle right here, is this a right triangle in there? Is that 90 degrees? I think intuitively you know that it is, and that's because this one right here is as well. So you should sort of have a, yeah, okay, I think that's going to be 90 degrees. So because it's 90 degrees, we can use basic grade 9 trigonometry, right? Sine is opposite over hypotenuse. What's the opposite? Here's the theta. So the opposite side is FD. Sine theta is FD. What is the hypotenuse? No, what is the hypotenuse, Nate? The hypotenuse of this 90-degree right triangle right here is FW, which is equivalent to mg. And when I rearrange that for FD, I multiply both sides by mg, and that, my friends, I really just did a formula derivation, really. Right? So the force down the plane is mg sine theta. The force down the plane is mg sine theta. And for exactly the same reasons, yep, cosine is adjacent over hypotenuse. The adjacent to this blue theta right here is Fn, Fn. And the hypotenuse again is Fw, which is equal to mg. And if you solve for Fn, Fn equals, that's a really bad rectangle, Fn, the normal force, is equal to mg cos theta. Those are the two you need to know. Kids always ask me, is the FD always the sine? And is the Fn always the cos? What do you think? Yes. Are you saying no because Nate said yes, or are you saying no because you believe it's no? The only way for that to happen is if we're talking about this angle right here, right? And that angle, Nate is right. That's why I asked if you're saying it because, yes. So in fact, it is that the real reason is because you always talk about the angle of the ramp as that one, right? You never say a ramp is angled at this number up here. Like it just never happens. Maybe if you find an obscure textbook or something, but 99.9 repeating times, I won't get into that today. It's that angle there, which matches this one here, which means that's always opposite. So yes, always, 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 FD is mg sine theta, and Fn is mg cos theta. Ready for a sample question? Yes, because that's what you really want to know, right? I don't care why it works, just give me a question that I can do. Here's a sample problem. Should I give you 30 seconds to jot it down? Let's do that. Okay, so I've got a 5-kilogram box at the top of a ramp. The ramp is angled at 30 degrees. I've put the box 1 meter up the ramp just for easy sort of figuring, and I've asked you to find a variety of things. In a test situation, I probably won't ask you to find FW, Fn, and FD because you're going to need to do those anyway. So I'm just sort of showing you the steps to get to something like this. Okay? Let's see if I can do this without my notes. Weight force. Easy. Mass times gravity. What was it? 5 kilograms? Is that what it was? 5 times 9.8. Look at me without a calculator. Oh, I'll have to do the kid thing. Ah, excellent question, Nate. Negative 9.8. Now, let me figure out. I think it's what is it? 4.9? 49. What am I saying? Okay. Nate's wondering if it should be negative. Now, let's go back to our original diagram here. Which way is this box going to be going? Down the ramp, right? Okay, down the ramp. If there was friction, and I haven't introduced any friction yet, if there was friction, which way would the friction be pushing? Up. Okay. Now, on a regular surface, when it's just flat like this, you've got usually an applied force that way and a friction force this way, and the friction force is negative, right? Yes, ma'am. Okay, so now, Nate, if I make down negative, then what directions are those? Something, right? Does it make sense to you that down the ramp we would call positive and up the ramp would we call negative? Does that sort of make sense to you that you would want to do that?
No, it should be right.
Usually, maybe, and that's fine too. Really, in this situation, you can define it any way you want. If you want down the ramp to be negative and up the ramp to be positive, that's okay.
Up and right, positive.
Whatever. But it can't be sort of this is negative here and this is negative here, right? Which way is the box going to be moving? It's going to be moving up and down the ramp, right? So we really want to assign our positive and negative to the possible directions that it's going to move. It's never going to fall through the ramp. So do I need to worry about that negative 9.8? The answer is no. What I really care is how big the weight force is. What's the magnitude? In this case, I don't care what direction it is. We know it's down, but we're not going to do anything with it, right? Okay. So now that I got my FW, next step is Fn, your brand new formula, mg cos theta, right? Did I already calculate the mg? Yeah, I did, right? Yeah, so it's going to be 49 cos 30. Yeah. $42.4? Normal force 42.4. Again, what direction is that? Well, that's kind of that weird.
I'm sorry. He's like watches something.
Okay. Glad you enjoyed that. What direction is that Fn? It's kind of that weird one, right? It's sort of up here, like this, right? Up to the left. I should draw it for those guys out there. Do we care about what direction that is? No. It's not going that way, right? We're just going to use it for friction a little later. So that's my Fn. Fd, our new friend. Fd is equal to mg sine theta. Fd is mg sine theta, which is 49 sine 30. I will tell you this. If you struggle with inclined plane problems at all, at the very least, you can find those three things because they're pretty much going to be, every problem is going to include them. 49 times 30 sine 24.5. That's what you said. Now, we've already sort of realized that we want a direction associated with that. Nate has insisted on down being positive. I'm not real comfortable with that, but I'll go along with it. What do you mean, when did you say that? Just like 5 minutes ago. Oh, yeah, you said the other way. Okay, so you want to, okay, so you want to make this negative. We defined that. You insisted. Negative 24.5. All good out there? Okay. Okay, last step here. So I got to find a net. Net acceleration. Now, did I say anything about friction here? It's a frictionless surface, and so my FD is in fact the only force that is up or down the plane, right? It's the only force there is, which means that the net force is the FD. That's the only force there is. If there was friction, like if there was a little bit of friction up, then I'd have to subtract that, right? We'll get to that. We did. We're going to use those eventually down the road here a little bit. Yeah. Okay, so my net force is my FD, which was it 30? 30, right? Was it at 30? Oh, 24.5. I don't have notes in front of me. Thanks. 24.5. You got to be a little bit comfortable with that, right? Because you keep in mind that the negative and positive is just a way of describing the direction. If you don't need to describe the direction, then don't worry about it. So, because F net is equal to MA, right? The net acceleration is caused by the F net. You can't say acceleration until you go through F net. No. Fn is mg cos theta. Normal force. Net force is mass times acceleration. Mr. Smigalski went through that with you the other day. So my 24.5 mass, I think, is 5. Am I right? And so my acceleration is 24.5 over 5. Well, I go by the rule, does it matter or not? In this case, it doesn't really matter. And we're back to, well, the only time you really got to worry about it is when there's opposite forces. One's to the left and one to the right, or one's down the ramp and one's up. When there's friction. There's no friction here. So you don't need to worry about it too much. So the acceleration down the ramp is 4.9 meters per second squared. Will the acceleration down a ramp ever be greater than 9.8? It can't be, right? Why is that? Well, the only way for it to be 9.8 is if the object is falling straight down, right? And if it's on a ramp, then it's going to have to be a little bit less. So your acceleration is always going to be some number less than 9.8. Because straight down, like dropping something straight down, is minus 9.8, right? So as you put on the ramp, it has to get less than that. If you're accelerating, I mean, if you're applying another force, this is just the force due to gravity, right? Like if you were in a car and you were driving down a hill, right, and like giving it gas kind of thing, then yes, you could, right? You'd be going pretty fast, pretty quick though, right? And let her go. Well, okay, so if you put it in neutral and let her go, what's the acceleration going to be? Right? It can't be any faster than that. In fact, it would be less because there would be friction, right? There'd be air resistance and quite a bit. So, yeah. Yep. Okay, so that is my acceleration. Time to get to the bottom. Now we're into the kinematics part here. I'm going to do it on the next page. Time to get to the bottom. My F is 4. Or my A is 4.9. Oh. Didn't want that. Don't want that just yet. Okay, I'm going to do it here. So time to get to the bottom. How far am I going? It was 1 meter, right? So D is a 1. My acceleration is that. What am I trying to find? Time to get to the bottom? D equals VIT plus 1/2 AT squared. We had so much fun in the first unit with this. Displacement is 1. What's the initial velocity? Did I say anything about that? What do you assume then? 0. Absolutely. Assume it's at 0. 0t, right? 0. Okay. Plus 1/2 acceleration, 4.9 t squared. Do you want it to be? It makes no difference. It really doesn't. Yeah, but it's going to be just a t squared one, right? So we're going to have 1 equals half of 4.9 is 2.45 t squared. 1 over 2.45 is t squared. So t is square root 1 over 2.45. That's a 2. Get over there. Help me out, someone. I might be able to do it here. One divided by 2.45. Oh, geez. 1 divided by 2. And then square root. 0.64? Is that? Did you get that? Anyone? Yeah. Okay. Good. 0.64 seconds. Time to get to the bottom. And there's one more question I think too, right? What's the last one there, Sam? Oh, how fast it's going at the bottom. You're dividing, Nate. To find I'll go a different color here. To find the speed at the bottom, VF equals VI plus AT. We're solving for VF. Initial velocity is a nice 0. Acceleration is 0.45. No, 49. 49. And time is 0.64 seconds. 4. Oh, it's 4.9. Yeah, right. Having a bad day today. And this board's not helping that it's not oriented properly. 4.9 times 0.64. 3.1. Does the fact that there's no friction here make it easy? Oh, yeah. Next stage is friction. We'll get there. Not today. No, not today. Not today. It'd be real nice. It's gonna be tricky to get there, but I know. You told me. I'm not gonna be here at spring break either. None of us are. We'll see. We'll see what happens, Nate. We'll worry about it later. Okay, now, note, here's a little aside. On a frictionless surface, do you agree that the net force is Fd? We've been through this, right? On a frictionless surface, the Fd is equal to the net force. So this means F net is equal to Fd. F net is equal to MA. Fd is equal to mg sine theta. What happens to the m's? And you'll see, just let me finish, Nate. You'll see that acceleration is equal to g sine theta. On a frictionless surface, the acceleration is g times sine theta, which makes it always less than, right? Therefore, do you guys know 3 dots in a triangle means therefore? Therefore, acceleration must always be less than 9.8, right? Because it's g 9.8 times the sine of theta. Okay. That's right. Yeah. You can use that to find acceleration. You can, in fact, I'm glad you picked up on that. Right? You can skip all this stuff because I want, you appreciate it a little bit more when you do it this way, right? G sine theta. We give you that 4.9. Okay? When it's frictionless, you can just go with G sine theta.
Exactly when you cook your own food, it tastes better.
Exactly. Okay, I have a handout here. I emailed it out to you guys. I hope you got it. I forgot to send it out ahead of time. I got a handout here with 4 questions on it. There is no friction, I don't think. No, there is. There's one with friction on it. Okay, and then there's some textbook questions as well that you should probably have a look at. So jot those numbers down there. Those are textbook ones. I'll hand this out. You guys should have this as well. I'll give you some time to work.